In this video, we are going to see about optical resonator. A laser is very much similar to an electronic oscillator. In an electronic oscillator, an amplifier tuned to specific frequency provided with positive feedback. When the oscillator is switched on, no noise signal of appropriate frequency appearing at the input will be amplified. The amplified output is fed back to the input and is amplified again and so on. A stable output is quickly reached and the oscillator acts as a source of particular frequency. In the case of low frequency, the feedback is again given. At frequencies, however, waves cannot be confined in wires and hence different kinds of feedback mechanism are to be used. At microwave frequencies, a closed cavity is used as an oscillator in which standing wave may be produced. However, at light frequency, the closed cavity cannot sustain the standing wave since the dimension of the cavity should be in order of the length. It is difficult to fabricate such microcavity. In next section, we are going to see about action of optical resonator. Light can be amplified by an active medium taken into the state of population inversion. Like an electronic oscillator, as discussed in the previous section, the input light is generated by the medium itself. A photon spontaneously emitted by an atom acts as an input and starts the stimulated emission. To sustain the stimulated emission acts and to increase the light intensity in a cumulative way, the following essential conditions are required. In first, we want to give positive feedback into the medium. Next, spontaneous photon emitted by atom independently in various directions produce stimulated emission in different direction. Emitting incoherent light. It means squandering away some of the advantageous feature inherent in the process of stimulated emission. An intense beam of light can be available only when the optical gain of the system exceeds the optical losses. A large radiation energy density is required to keep the stimulated emission dominating over the spontaneous emission. Those requirements are met with the help of an optical resonator, which can be understood with the successive stages shown in the figure. Through a suitable pumping mechanism, the medium is taken in the state of population inversion. Now a large number of atoms in the excited state may be decay spontaneously and emit photon in various directions. Each spontaneous photon can trigger many stimulated transitions along the direction of its propagation. As the initial spontaneous photons are emitted in different direction, the stimulated photon will also travel in the different direction. Many of them would leave the medium without reinforcing the strength. However, if the mirror is placed at the end of the active medium, a specific direction is imposed on the photon. Photons propagating along the optic axis of the pair of the mirrors are augmented, whereas photon emitted in any direction will pass out of the sides of the resonator and are lost as shown in the figure. A majority of photons traveling along the optic axis are reflected back on reaching the end mirrors. They propagate toward the opposite mirror and on their way they stimulate more and more atoms and build up their strength. The photons that strike the opposite mirror are reflected once more into the medium. The photons will travel along the axis, generating more photons and cause more and more amplifications. As the photons are reflected back and forth between the two mirrors, the stimulated emission sharply increases and the amplification of light is augmented. At each reflection at the front end mirror, light is partially transmitted through it. The transmitted component constitutes a loss of energy from the resonator. When the loss at the mirrors and within the medium balances the gain, the laser oscillation build up and the laser output will become bright. As the in mirror reflect light strongly into the laser medium, the radiation density is large within the medium and sustain the stimulated emission. In general, the active material has a few lasting transitions rather than only one. It is desirable that the laser oscillates at one frequency and produces monochromatic light. It requires suppression of undesired transition. This is achieved by the coating mirrors with suitable material which highly reflect the photon of the desired frequency and at the same time absorb the photon of the desired frequencies. These are the explanation for optical resonator and action of optical resonator. Thank you.
We will see about ND arc laser. ND laser is a neodymium based laser. ND stands for neodymium rare earth element and ARC stands for yttrium aluminum garnet, which is Y3Al5O12. It is a 4-level solid state laser. It's a principle for neodymium laser. The active medium ND arc laser is optically pumped by krypton flash tube and neodymium ions ND are raised to excited level during the transition from metastable state to ground state. Laser beam of wavelength 1.064 is emitted. This diagram for ND arc laser. Instruction for ND arc laser. In the active medium ND arc crystal, a small amount of yttrium ions Y power 3 is replaced by neodymium ions Nd power 3. The active element is cut into a crystal rod. The laser rod and a pumping source flash tube are placed inside a highly elliptical reflector cavity. The flash tube is controlled with the help of the capacitor. The end of the rod are polished and made optically flat and parallel. The optical resonator is formed by using two external reflecting mirrors. It is a working for ND arc laser. When the crystone flash tube is switched on, the neodymium atom are raised from the ground level E0 to upper level E3 and E4 by the absorption of radiation of wavelength 0.73 and 0.08. Photons thus generated travel back and forth between the two mirrors and grow in strength. After some time, the photon number multiplies more rapidly, for enough strength has been attained. In the instant laser light of wavelengths 1.06 emitted through the reflector, it corresponding to the transition from E2 to E1. The transition from E2 to E0 is rapid and non-radioactive. This is energy level diagram for ND arc laser. Characteristic for ND arc laser. Type: it is a 4-level solid state laser. Active medium: the active medium is a ND arc crystal rod. The pumping method: the optical pumping is employed for the pumping action. Pumping source: xenon or krypton flash tube. The nature of output is pulsed or continuous beam of light. Wavelength of output beam is 1.06. This is advantages for ND arc laser. It has high energy output. It has very high repetition rate operation. It is much easy to achieve population inversion. ND arc is a crystalline material and has corresponding line width is much smaller, which implies much lower threshold. This is disadvantages for ND arc laser. Application for ND arc laser. It find many applications in range finders and illuminators. It is widely used in engineering applications such as register trimming, scripting, micromatching operator. Thank you.
We are going to discuss about the topic of laser cutting. Cutting is one of the most popular laser material processing. High power laser beams like laser beam emitted from CO2 laser are used for cutting hard substances like steel. What is high power laser beams? The definition of high power laser beam is lasers emitting very high optical powers. It can be from 500 megawatt to 12,000 megawatt. While the low power laser beams are usually used for cutting plastic, fabric, etc., it is very accurate and precise cutting tool. Laser cuttings depends on the input power and it is directly proportional to the thickness of material to be used for cutting. If the laser beam is used to focus on the metallic target, the target gets vaporized without leaving any material distortion of the target. We know different types of material are used along with the laser beam. Usually, oxygen is used for cutting. If the combination of gas along with the laser beam is blown coaxially, the target metallic substance get vaporized. Therefore, the gas reduces the power of the laser beam required for cutting. Next picture, we can see the diagram of laser cutting. We can able to see here lens, laser beam, nozzle, workpiece, gas jet and gas inlet. The advantages of laser cutting. It is very accurate and precise. No contamination of target material. No warping of target material. This is the advantages of laser cutting and this is applications of laser cutting. Laser cutting has become an increasingly popular method for cutting materials such as metal, plastic, wood and glass. Disadvantages of laser cutting. Limitations on material thickness, harmful gases and fumes, high energy consumption and upfront costs. This is the real images of laser cutting. Cutting application of industry. In this blog we will be discussing the top 7 industries that use laser cutting technology. These include the automotive, construction, electronics, medical, military and metalworking industries. This is also a real images of laser cutting and this is the wood laser cutting.
In this video, we are going to talk about propagations of light through an optical fiber. Introduction. It was demonstrated by the British physicist John Tyndall in 1870. He stated that the light can be guided along the curve of the stream of water. Due to the total internal reflections, light get confined to the water stream and the stream appear the luminous. A luminous water stream is considered in optical fiber. In 1950s, the transmission of image through the optical fibers was released in practice. Next, the optical fiber. Definition. An optical fiber is cylindrical waveguide made of transparent dielectric glass or clear plastic which guide light waves along its length of total internal reflections. It is very thin like human hair, approximately 70 micrometer or 0.003 inch diameter. The thin strand of metals is called wire and a thin strand of dielectric material is called fiber. This is total internal reflections and this is the optical fiber. Principle. The light propagated in optical fiber from one of its end to the another end is based on the principle of total internal reflections. When the light enters the one end of the fiber, it undergoes successive the total internal reflection from one side walls and travel down the length of the fiber along the zigzag path. A small fraction of the light may escape through the side walls but a major fraction emerge out from the exit end of the fiber. The light can travel through the fiber even if it is spent. Next, the cladding perform the following important functions. keep the size of fiber constant, and reduce the loss of light from the core into the surrounding air, protects the fiber from the physical damage and the absorbing surface contaminants, prevents leakage of light energy from the fiber through the emanated waves. The optical fiber system. An optical fiber is used to transmit light signal over long distance. It is essentially the light transmitting the medium. Its rule beginning very much similar to coaxial cable or waveguide is used in the microwave communications. Optical fiber requires a light source for launching light into the fiber at input end and the photodetector to the receive light at the output end. As the diameter of the fiber is very small, the light source has to be dimensionally compatible with the fiber core. Light emitting diodes and laser diodes, which are very small in size, serve as the light source. Next, the total internal reflections. A medium having a lower refractive index is called rarer medium, while the medium having a higher refractive index is called denser medium. Propagation of light through an optical fiber. The diameter of optical fiber is very small. We cannot use bigger light source for launching light beam into it. Light emitting diode and laser diode are the optical source used in fiber optics. In case of the small size source, a focusing lens has to be used in concentrate on the beam of the fiber. This is the diagram of optical fiber. This is core and this is cladding. Sin theta c equal to n2 divided by n1. Next we are going to acceptance angle. Considering a stepped index optical fiber into which light is launched in at one end. Let the refractive index of the core be n1 and the refractive index of the cladding be n2. n2 less than n1. Let n0 be the refractive index of the medium from which light is lodged into the fiber. This diagram of the acceptance angle. If theta I is increased beyond the limit, pi will be dropped below the critical value pi of c and the ray escapes from the side walls of the fiber. The largest value of the theta I occurs pi when pi equal to pi of c. In tel APC, sin theta r equal to sin 90 degree minus pi equal to cos pi. This is equation number 2. Using equation 2 in 1 we get sin theta I equal to n1 divided by n0 cos pi. This is equation number 3. Pi equal to pi of c. Sin theta I maximum equal to n1 divided by n0 cos pi of c. Sin pi of c equal to n2 divided by n1. Cos pi of c equal to root of n1 square minus n2 square divided by n1. Sin theta I maximum equal to root of n1 square minus n2 square divided by n0. Theta I maximum equal to theta naught. Sin theta naught equal to root of n1 square minus n2 square. Theta naught equal to sin power minus 1 root of n1 square minus n2 square. This is the diagram. Next we are going to numerical aperture. The numerical aperture NA is defined as the sine of the acceptance angle. NA equal to sin theta naught. Sin theta naught equal to root of n1 square minus n2 squared. Therefore, NA equal to root of n1 square minus n2 squared. n1 square minus n2 squared equal to n1 plus n2 and n1 minus n2. n1 square minus n2 square equal to n1 plus n2 divided by 2 and n1 minus n2 divided by n1 into 2n1. n1 plus n2 divided by 2 approximately n1. n1 squared minus n2 square equal to 2n1 square tel. Na equal to root of 2n1 square tel. Na equal to n1 root of 2 tel. The numerical aperture determines the light gathering the ability of fiber. It is a measure amount of light that can be accepted by the fiber. This is our diagram. And thank you for watching the video.
In this video, we are going to see splicing of optical fibers. So what is splicing? Splicing of optical fibers is a technique used to join two optical fibers. This technique is used in optical fiber communication in order to form long optical links for better as well as long distance optical signal transmission. Splicers are basically couplers that form a connection between two fibers or fiber bundles. Splicing techniques of optical fiber. So there are two splicing in optical fiber: fusion splicing, mechanical splicing. In mechanical there are two: V-grooved splicing, elastic tube splicing. Fusion splicing. So what is fusion splicing? Splicing any fiber by making use of the fusion technique provides a permanent contact between the two fibers. In the fusion splicing, the two fibers are thermally joined together. In this particular technique, an electrical instrument is necessarily used that acts as an electric arc so as to form a thermal connection between the two. So the figure below shows the fusion splicing of optical fiber. So there are two fiber holder and an electric arc. So the fiber is to be placed on the holder. Then the fusion splicing starts. So this is the fusion splicing of optical fiber. Next is the mechanical splicing. So the following two categories comes under mechanical splicing. First is the V-grooved splicing. In this splicing technique, initially a V-shaped substrate is taken and the two fiber ends are buttered in the groove. Once the two gets placed inside the groove in proper alignment, then they are bonded by an adhesive or index matching gel. This adhesive provides proper grip to the connection. So the figure shows the V-groove optical fiber technique. So there is a V-grooved substrate. There is a fiber at the middle. So there is a clamping of fiber ends. So this is the V-groove optical fiber technique. So second one is the elastic tube splicing. It is a technique of splicing the fiber with the help of the elastic tube and majorly finds its application in the case of the multi-mode optical fiber. The fiber loss in this case is almost similar to that of the fusion technique. However, the need for equipment and skill is somewhat less than the fusion splicing technique. So the figure below shows the elastic tube splicing technique. So there is an elastic material with axial alignment. So there is a capillary tube. The fiber is being inserted and the inserted fiber is getting out. So this is the elastic tube splicing technique. Next is the advantage of fiber splicing. It allows long distance optical signal transmission, less reflection at the time of signal transmission. Splicing provides almost permanent connection of the two fibers. So there are three advantages of fiber splicing. Disadvantages of fiber splicing. Sometimes the fiber losses are very much higher than the acceptable limits. Splicing increases the overall cost of the optical fiber communication system. So there are two disadvantages in fiber splicing. Thank you.